Okay, let's dive right into this explainer. Have you ever really thought about the sheer, staggering challenge of keeping a massive ship parked in the exact same spot in the middle of a violent ocean for 25 straight years, and doing it without ever disconnecting? Well, that is exactly what floating production, storage, and offloading vessels, or FPSOs, do. They're absolute marvels of modern engineering, but their entire existence hinges on solving this incredibly hostile problem. How do you remain completely stationary to extract oil and gas from the crushing depths below, no matter what the weather throws at you? By the end of this explainer, you're going to understand the exact mechanics behind how this is actually achieved. We're going to cover single point versus spread mooring, the design standards and components used to anchor these beasts, how complex turrets and swivels enable a ship to practically dodge a storm, how calm buoys allow shuttle tankers to offload safely, and finally, the incredible construction of deepwater risers.
To really understand how engineers solve this seemingly impossible problem, we're going to break the hardware down into 5 structured sections: mooring, designing for the storm, the art of weather vaning, calm buoys and offloading, and deep water risers and pipes.
All right, part 1, mooring, holding fast.
So, let's start from the bottom up. Think about it. The ocean is this hostile force that is constantly trying to rip the FPSO away and snap its delicate underwater pipes. Holding it perfectly on location is our ultimate adversary here, because unlike conventional tankers that can just detach and run to port or go to dry dock every few years, an FPSO stays on location for the entire lifespan of the oil field. That means the mooring system has to have absolute, uncompromised reliability.
The foundation of all that reliability comes down to picking the right mooring strategy from the get-go. Here's the fundamental difference you need to know. Spread mooring uses a passive spread of static lines attached to the bow and stern. It's relatively simple, but it restricts the ship from turning, making it really only suitable for more benign waters like the deepwater locations off West Africa or Brazil. Single-point mooring, on the other hand, acts as a central pivot for treacherous storm environments. It secures the vessel at just one point, which is an absolute necessity when you need protection from heavy seas and super strong currents. Now think about how these lines actually drape down to the seabed. They aren't pulled super tight like guitar strings. Instead, these catenary lines act like massive springs rather than rigid tethers. The combined weight of the huge chains and anchors creates this natural stiffness that lets the vessel absorb massive wave energy. In fact, this built-in flexibility allows an excursion rate, which is basically a controlled drift, of up to 30% of the water depth. The real genius here is that the ship can move just enough to survive without stretching or snapping the critical oil risers running down below. Moving on to part 2, designing for the storm. To absolutely guarantee a vessel won't break loose, engineers have to follow incredibly strict guidelines, like the EPCI RP2SK standards, to calculate the maximum line tensions and anchor loads. And the crucial takeaway here is that engineers mix materials strategically to meet these extreme requirements. They don't just use one type of cable for the whole thing. They use heavy, highly durable studless chain for the really abrasive seabed and for the connection points on the hull. But chain is just way too heavy for the entire length in deep water, so they transition to spin-resistant wire rope to span those deep sections. This combination brilliantly balances restoring force, abrasion resistance, and overall weight.
Putting this massive puzzle together out at sea is a highly calculated operation. To ensure survival, the installation has to happen in phases. Anchors and chains are often laid out before the FPSO even arrives on site. Once the ship hooks up and winches the chains through its hull, we reach the most critical step of all. The crew conducts a brutal test where every single line is stressed to 100% of its maximum storm load for at least 15 minutes. This instantly proves the anchor's holding power, it checks for any damaged components, and it permanently eliminates any slack in the chain resting on the seabed. It's a literal trial by fire, or, well, sheer tension.
All right, part 3, the art of weather vaning. So, with the ship securely anchored, how does it actually survive the constantly changing direction of wind and waves? The answer is weather vaning. It's the ultimate survival mechanism for single-point moored vessels. Just like a weather vane on a barn roof spins to point right into the wind, the entire massive FPSO ship freely rotates around its mooring point. And this is such a brilliant illustration of how we work with the ocean rather than trying to fight against it. By turning its bow directly into the oncoming weather, the ship just slices through the elements, which drastically reduces the massive environmental forces slamming into its broad sides.
The hardware that makes all this rotation possible is called the turret. It is essentially a giant cylinder that the ship is built entirely around. The turret is chained to the seafloor and remains completely stationary while the hull of the ship rotates around it on these massive bearings. Turrets can be large, permanent structures integrated directly through the internal hull, or they can be buoyant, disconnectable units that can actually drop away if the ship ever desperately needed to escape a catastrophic event, like a massive iceberg. But here is the multi-million-dollar engineering riddle. If the ship spins 360 degrees, potentially endlessly in one direction, why don't the subsea oil pipes running up from the ocean floor twist, tangle, and just snap? Well, the answer is this towering, incredibly complex piece of machinery called the swivel stack. It's mounted at the top of the turret, and it consists of fixed inner rings connected to the seabed and rotating outer segments attached to the ship's decks. It seamlessly transfers high-pressure oil, gas, and electrical signals across a rotating boundary. It is a total masterpiece of engineering. Even though its tight, high-pressure seals still remain one of the biggest limiting factors in ultra-deep water production today.
Which brings us to part 4, calm buoys and offloading. So we have the oil safely extracted and stored on board, right? But now we have to actually transfer it to a transport vessel, a shuttle tanker. Offloading oil directly from the back or stern of an FPSO into a tanker during a severe storm is a terrifying recipe for disaster because you risk a massive collision between two huge steel giants. This is exactly where catenary anchor leg mooring or calm buoys come into play to overcome these severe operational limits. By using a buoy situated pretty far away from the FPSO, shuttle tankers can safely hook up and load oil even in incredibly harsh conditions, and we're talking operations in 80-kilometer-per-hour winds and massive 5.5-meter waves.
If you follow the path of the oil, you can really see the genius of this setup. The oil is piped away from the FPSO, runs along the seabed, and then goes up into the floating calm buoy. The shuttle tanker then ties up securely to this remote buoy and attaches floating hoses. And because the buoy acts as its own miniature single-point mooring system, the tanker is free to weather vane completely independently from the FPSO. It creates this safe, isolated buffer zone that keeps the entire global supply chain moving, absolutely regardless of bad weather.
And finally, Part 5, Deepwater Risers and Pipes.
Let's look at the crucial lifelines bringing the oil up from the seabed. You've got to remember that the FPSO is constantly heaving. It's rising and falling with the massive ocean waves. If you just dropped a straight pipe down to the well, the massive upward pull of the ship would rip the pipeline right off the seabed. There's no way it would survive. To prevent this, engineers shape the risers into very specific geometries, like the steep S and lazy wave configurations. By attaching submerged, highly buoyant structures called mid-water arches to the pipes, they create these deliberate slack loops. These loops absorb all the kinetic energy and heave of the ship, perfectly isolating those fragile seafloor connections from the chaos happening above on the surface.
And the pipe itself, it's definitely not just some simple rubber hose. For dynamic movements in deep water, we rely on highly specialized, unbonded, flexible pipe. It is built layer by meticulous layer to survive the extreme crushing pressures of the deep ocean, the high bursting pressure of the oil inside, and the constant, punishing bending fatigue caused by the ocean waves.
If we literally peel away the layers of the pipe, we see this amazing mini-narrative of survival. The innermost layer is a steel carcass that prevents the pipe from collapsing under the massive weight of the ocean. Next, an extruded polymer sheath securely seals the oil inside. Surrounding that is interlocking pressure armor, followed by counterwound layers of tensile wire to fight off the intense bursting pressures and stretching forces. Finally, anti-wear polymer buffers and an outer sheath protect the entire assembly from seawater and abrasion. Every single layer has a highly specialized, absolutely critical job. If just one fails, the entire system is at risk.
We've seen just how incredible the current engineering is, from heavy mooring chains to the intricate layers of a flexible riser. But you know, as the easy oil runs out, we are moving further and further offshore. Which leaves us with a really fascinating final question. As FPSO operations push into ultra-deepwater frontiers, well past depths of 1,000 meters, what new radical gathering system designs and materials are going to be required to survive the crushing, icy depths of tomorrow's energy landscape? Thanks so much for joining me on this explainer, and keep questioning the engineering all around you.